are we today? 18, is that right? Anybody keeping track for me? Okay, day 18. I think based on comments that were made here in class the other day, we probably need to stop and spend a few moments on some questions from homeworks that we've have been assigned to you recently that maybe gave you grief as you went through the problem, and just in case you see it again, which might happen, we need to get it cleared up. So I think we need to dig back to section 2.3 to clear up some homework problems, possibly 2.4. We'll see how far we get. We will plow into chapter 2, section 5 today, where we start to get that concept of derivative. It's not really called that yet. It's called the slope of the tangent line to a curve. But we'll at least begin that today. And what we don't get to in 2.5 today, we will finish tomorrow. So 2.3, problem set, looking at page 117. So I guess actually on page 117, since we can start there with a couple of potential problems and then move on. Did somebody say problem 8 before class was started?
8A.
Yes. 8?
A.
Part A?
Yeah.
Okay. And we might also take a quick look at B. I think these two are somewhat inseparable. So part A, what is wrong with the following equation? I'll just go ahead and put a question mark there in front of the equal or over the equal sign. So we're considering, are they equal? And if they're not equal, what seems to be the problem? Well, probably this numerator needs to be factored. And I imagine that x minus 2 is a factor. And I would imagine that x plus 3 is the other. Is that correct? So it looks like we can just kind of slash the x minus 2's and say, gosh, they are equal. And if we, really didn't care about being right or wrong today, we could do that. But why can we not just mindlessly slash the x minus 2's?
Because x can be 2.
And if that were true, what would we be saying?
0 over 0.
Right, we would be saying that 0 over 0 is 1, right?
Mm-hmm.
So you can do this. You can say x minus 2 over x minus 2 equals 1 as long as x is not exactly 2. But that little disclaimer is what the difference is in this problem, is that you cannot get rid of x minus 2 over x minus 2 because is there a possibility that x could be 2? Yes, there is. And we would be saying that 0 over 0 is 1. Is 0 over 0 1? Yes, it is. But what else is it?
So you're not.
It's also 11 and 4 and 7 and negative 13. It's anything you want it to be. So for us to say that 0 over 0 is 1 is too confining. So it's about anything you want it to be. So we can't say it's 1 when there's a possibility it might not be 1. So has the distinction been made then between the left side and the right side? The distinction is that we cannot be 100% sure that x is not 2. Therefore, when x is 2, if x were to be allowed to be equal to 2, then the left side would be what? 0 over 0? And we could not really say that that's x plus 3. Anytime you have 0 over 0, basically it means whatever you're trying to do with that problem, scrap it because it's not working, and try some other method. So left side and right side are not equal because of that single bad value x equals 2. Part B, in view of Part A, explain why the equation, the limit of the left side and the limit of the right side are in fact equal. I think that's probably worth considering. These two are not equal. Now, can you tell me how they differ? If I were to sketch this function and sketch this function, how would they be different? Well, we know there's only one bad value. That's a 2. Since x can't be 2, y in this one, y will never be 5. Is that right? How did I get that?
2 closer.
Because they're equal except for that bad value of 2. And if x could be 2 over here, y in fact is 5. X cannot be 2 over there, therefore y will never be 5. So this function, if we graphed it, as long as x is not 2, we can get rid of those. And it is the line y equals x plus 3. But since x can't be 2, we delete the point 2, comma, well, since x can't be 2, y will never be 2 plus 3. Never get 2 in that position. So what have we called that before?
Removal?
Okay, it's removable. And what is it? It's a hole in the graph. And what is this thing?
Discontinue.
The line, isn't it? Y equals x plus 3 is a line. And we delete that point, so it's a line with a hole in it. So x plus 3 has a y-intercept of 3 and a slope of 1. So we come up here to 2. Drop that point out, take a little intermission there. So there's this function. Suppose g of x is the other thing, just x plus 3, the right side of the equation. What would it look like? Line with a hole in it? Just the entire line, right?
Yeah.
So do you see how they're alike? Well, they're the same line with the same y-intercept. One has a hole in it at point 2, comma 5. The other one is the entire line. Now, part B says, what happens as we get closer and closer and closer to 2 in each picture? In this picture, we close in on 2 from both sides. What is the y value getting closer and closer to? 5. Now, the fact that we never get there is not an issue. We get closer and closer to 5. That's what a limit means. And here, what's the limit of the g of x as x approaches 2? What are we getting closer and closer to?
5.
Also 5. Now, we actually get there here, but does that matter? We don't care what happens at x equals 2. We care what happens as x approaches 2. So are we converging on the same value in both functions? Yes, we are. In one of them, we don't get there because a point was deleted. In the other one, we actually get there. But it doesn't change the limit answer. So even though the functions themselves are slightly different, the limit of those two different functions is the same as x approaches 2. Is that okay? Does that suffice for 8? Shanti, did that answer your questions? Next page, 118. Any issues?
On that same page, number 4.
Oh, same page, number 4. Sorry, back up. Page 117. Evaluate the limit and justify each step by indicating the appropriate limit laws. This is probably at this point in time, since we're well beyond this material, I don't know how much we need to break it down into pieces. But we can do the limit. Is there a problem with putting 2 into this function? Doesn't look like it's a problem in the numerator. Is there a problem with putting 2 in the denominator? 2's not a bad value, is it?
No.
Not on this one, I don't think. Now, what would your hesitancy be? How would you determine that 2 is a bad value?
Make 0 in the denominator.
0 in the denominator, maybe. Sometimes when we get just 0 in the denominator, let's suppose we got 4 over 0. Would that be an answer? Would we have to massage that problem? Or could we go directly to an answer? What is 4 divided by 0?
0.
Undefined? Therefore, the answer would be no limit, right? The real problem is what? 0 over 0. So do we get 0 over 0? We don't. So there's nothing wrong in this case with just substituting 2 in. I think this is the kind of thing they wanted, that this is the limit of a quotient. And I know we perceive this to be overkill right now. Limit of a quotient is the quotient of the limits. And then you could break this down further by saying the limit of the sum is the sum of the limits so these are limit laws. Overkill?
Yes.
Yeah, probably at this point. Now, there's more we could do also. We could do 2 times the limit of x squared as x approaches 2. Limit of x squared, x approaches 2. Limit of 6x would be 6 limit of x as x approaches 2. So I think that's the kind of thing that we're at least supposed to go through one time. I think that's why I picked one problem. Somebody had your hand up.
Oh, yeah.
Yes.
Oh, so if it's a number over 0, does that always mean that there's no limit?
That's right.
But if it's 0 over 0, it means you can do something with
Yeah,
it.
right. That 0 or 0 is never an answer. It tells us that we've got to do something else. But something over 0 means that the limit does not exist. Or as we worked with yesterday, if we want a description of what happens to the y values, it's either positive or negative infinity. But the best answer is does not exist. So the final step in this would be to just what? Let x be 2, right? No problem with the substitution. But at this point in time, we've gone well beyond this. This problem almost looks kind of silly, right? To break it down, quotient of the limit. Limit of a quotient is the quotient of the limits. Limit of a sum is the sum of the limits. Anytime you have a coefficient here, it's okay to farm that out in front. It's a little bit too much. Served its purpose when we went through this, but we've gone beyond that now. Page, so let's get an answer here before we leave it. Numerator would be what? 9.
9 over 12.
Denominator,
12.
12.
3/4.
3/4. Is that okay? So what's wrong with the original problem? Just plugging into, and nothing's wrong with that. Nothing wrong at all. But I think they wanted us to do a little bit of this. this right here, just so we could get a look at what's legal with limits and what's not legal. Okay for that one? Page 118. What do we need to look at there? 12. Difference of two cubes, one of the reasons I picked it out. X cubed minus 1 cubed, that's the difference of two cubes. And down here we've got the difference of two squares. Can we just substitute 1 in the numerator and 1 in the denominator? Well, we could, but we don't get very far because we get back to that 0 over 0, which means we've got to do something else. What can we do in the numerator? And we addressed this when? Yesterday?
Yesterday.
Yeah.
Right? Difference of two cubes. Since 1 is a root, x minus 1 has to be a factor in both numerator and denominator. If I want to make a stab at that trinomial in the numerator, what is it? What did we decide yesterday?
Square.
X squared plus x plus 1, right? And if for some reason you distrust that, multiply it out, right? And you should get x cubed minus 1 out of the numerator. And the difference of two squares in the denominator is that. As long as x is not 1, what can we get rid of? X minus 1 over x minus 1 would reduce to 1, as long as x is not 1. X is not 1, so we don't have to worry about it. Now that we've gotten by the potential bad value, we no longer have 0 over 0. Is it okay to let x take on a value that's so close to 1 that for all practical purposes it's 1?
Yeah.
Let's pick a number. How about 1? That's pretty darn close to 1, right? So what do we get in the numerator?
3.
3.
Over
3
2.
Over 2.
over 2.
Yeah.
Now, if you pictured this function on your graphing calculator, this original function, x cubed minus 1 over x squared minus 1, and you looked at it on your graphing calculator and you tried to look at the graph real close to the x value 1, you should be able to get a readout of what? 3 halves, 1.5. Now, at 1, it doesn't exist. But near 1, you ought to get real close to 3 halves. Is that okay for 12? That this numerator is the reason why I chose that problem, is so we could get a little practice factoring the difference of two cubes. In general, the difference of two cubes the first factor is the binomial, the thing that's being cubed in the first position minus the thing that's being cubed in the second position. And what would the trinomial be? It's got to be a squared, right, to get a cubed. And back here it's got to be b squared to get b cubed. And this has got to be positive, right? What's the middle term?
AB.
AB. Is this factorable? Is that trinomial factorable? It's not. So that's in fact why we have a binomial and a trinomial. The trinomial is irreducible. So we're kind of stuck with that. We didn't come across this yet, but we will sooner or later. The sum of two cubes also factors. I don't think we've come across this, have we? A cubed plus b cubed. Now we know a squared plus b squared does not factor, but a cubed plus b cubed does factor. What do we need here? We need an a squared here. We need a b squared here. And it's a minus ab in the middle. And if you doubt either one of those, you can multiply it out, and you'll see that the first one you do get a cubed minus b cubed, and the second one you do get the sum of the two cubes. So if these are something you haven't seen for a while, it might be Andy to jot those down, and we see them again. It's not like we're seeing it for the first time. Okay, anything else? Page 118. Which one?
Number 30.
30? Somebody else say something?
18.
18? All right, let's get 18 first. You know, I don't need to say that I like problem 18 because I picked 18 out. Obviously, there's something about it that I think is valuable. Let's do 18 and 30. And then we'll see where we stand time-wise, see if we can go on to the next section. 3 plus h, and here's why I chose it, to the negative first. 3 to the negative first. Not just the interpretation of the negative exponent, but what results after we interpret it. Now, take a look at this problem. We're going to do some things in the new material that we're going to cover today. They're going to look a whole heck of a lot like this. And we're not going to be handed the problem. We're going to generate this kind of problem on our own. We're going to start off with a function, 2 points on the function, let the 2 points get closer together, and our answer is going to look a lot like this. 3 plus h to the negative first. What is that?
1 over 3 plus h.
Okay. 3 to the negative first is 1 over 3. Suggestions, recommendations. What do we need to do? The difference of two fractions. Least common denominator in the numerator. So we're going to work in the numerator. Denominator's fine. It's h. You're not going to simplify that very much. The numerator is the difference of two fractions. So the common denominator would be their product. So we need a 3 here in the bottom. So I can't just manufacture a 3 in the bottom without also multiplying the top by 3. What does this fraction need? It needs a 3 plus h. I can't just manufacture that in the bottom. So each of those fractions I just multiplied by what?
3 plus h.
Okay, 3 plus h over 3 plus h, which is what? 1. Right? Is it legal to multiply something by 1? Sure is. And the other one I multiplied by 3 over 3. Is that legal? 3 over 3 is also 1. So anytime you multiply by 1, that's legal. So that makes the numerator 3 over, you can skip this step, by the way. That's the numerator. Everybody agree with that? And the purpose was to get a common denominator so we can combine these two fractions. Now, we've also got division by h. Can I also accomplish that by multiplication by 1 over h? Now, why would I do that? Well, you don't have to do that, but I don't like complex fractions if I can avoid them. Fractions within fractions. So to avoid the complex fractions, let's just multiply by the reciprocal of the denominator. So these have the same denominator, so let's go ahead and combine them. So that's 3 minus 3 plus h, all over that common denominator. And I'm probably writing too much here, but I don't want to skip a step in case somebody has a question about this simplification, because we're going to need this as we progress through the end of chapter 2. So 3 minus 3, they knock each other out. And then we've got a minus h. Is that okay? In the numerator? Now, can I just take this h and multiply it by the denominator? Right? Isn't that how you multiply fractions? You multiply across the top, and then you multiply across the bottom. So I'm going to multiply the top by 1 and the bottom by h. Now, did I miscopy this? Yes, I did. Should have caught that. This is h approaching 0. I could lie to you and say I did that to see if anybody would catch it. But you know better than that. That was just a mistake. Is it okay to let h be 0 at this point? No.
No.
No, no.
In fact, up to this point, any point in this problem, including this point, we can't let h be 0 because we'd have 0 over 0. But as long as h is not 0, anything reduces over itself to 1. So here's what we have. The limit as h approaches 0 and now is it okay to let h be very, very, very close to 0?
Mm-hmm.
So close to 0 that for all practical purposes it is 0. And what would we get if h were allowed to take on the value 0?
Negative 199.
Negative 190. Now, that's very, very difficult to tell from the original problem. I think virtually impossible to tell from the original problem. You've got to get the fractions, get a common denominator, combine the two fractions. I mean, you've got to go through that process. But the result of that is negative 1 over 9. Questions on that? Hopefully I didn't mess you up here with my miscopy. And what was the other? 30? We need to look at 30. Is that okay for 18? Move this aside. Page 118, number 30. Directions: find the limit if it exists. If the limit does not exist, explain why. Well, let's look at this function. This absolute value x minus 2 over x minus 2. And we care what is happening to this function near x equals 2. Now, is it 2 kind of a transition point for this function? If you put in numbers larger than 2, does the absolute value really have any meaning? The numerator is positive, the denominator is positive. So if I pick a value greater than 2, and I know I got to stay away from 2, I could plot points, and the x value, the numerator and the denominator would be the same. So if I just pick a value, let's say 2.1 or 3 or 5, some value larger than 2, 2.1 minus 2, 2.1 minus 2, they're the same, right? Numerator and denominator. 5 minus 2, 5 minus 2. What's the answer in each case? 1. If x is less than 2, now there is a difference, right? So a little bit less than 2, I'm just putting in 1.9. So the numerator is 1.9 minus 2 absolute value. That's what? Positive. What, 1/10? The denominator is 1.9 minus 2, which is negative 1/10. So what's positive 1/10 over negative 1/10? Negative 1. Is that the same as true for 1 and 0, right? All of these are negative 1. So values to the right of 2 are all positive 1. Values to the left of 2 are all negative 1s. Does that look like a reasonable picture, what we're dealing with? And we want to know what's going on this function as x is allowed to approach 2 from both sides. I like that quick answer. I see the heads shaking. Means what?
No good.
It does not exist, right? And tell me why that it does not exist.
They don't reach the same.
Okay, we're not closing in on the same value from either side, are we? As we come in from this side, we're up here at positive 1. As we come into 2 from this side, we're coming into the x value 2, we're coming in at another level. So we're coming in at 2 different levels, therefore there is not a limit. Now, can I split this out? I don't want to leave this problem yet. Can I split this out into 2 one-sided limit questions
Yeah.
and expect to get an answer? So what's the first one say? Coming in from the right, is that correct? Is there a limit as we come in from the right? What is it? 1. Is there a limit as we come in from the left? Negative 1. And therein lies the problem, right? We don't have the same limit from both sides. Therefore, the answer to the 2-sided limit question is does not exist. That suffice on 30. Are we leaving anything unanswered here on this problem set, 2.3? Okay, is there a quick and easy one in 2.4 that we could look at? It's going to be too time consuming, I may table it and get to it later. So I'm looking at page 128, 129,
16.
16. I think we can look at that one and then maybe get a start into the new material. So are there others that we need to come back to from 2.4? Which one? 18 and 20?
37.
Okay, so we've got some. All right, well, let's look at 16 and we'll come back to the others. So we're looking on page 129, number 16. Looks like we've got a split domain function. Looks like we've got a piece of a parabola. And it looks like 1 is the kind of the transition point in the domain. So for a while we graph 1 plus x squared, and for a while we graph 4 minus x. So when you look at that or you write that down, do you see that we're going to graph a piece of a parabola and a piece of a line? Is that what you see? Okay, and that transition point where it stops being a parabola and starts being a line, or vice versa, is x equals 1. So the first line, x has to be less than 1. And the second line, x can be greater than or equal to 1. So let's start over here. Since x can be 1 or anything larger, if x is allowed to be 1, which is legal, what's the corresponding y value? 3. If x were 2,
2.
and if x were 3, just linear, right? That's the linear piece over there to the right. Over here, I know we're not supposed to let x be 1. I'm going to go ahead and kind of fudge on that a little bit and say I'm going to let x be 1, but then I'm going to come back and delete that point. So if x could be 1, which it can be very, very close to 1, but not quite 1, but if x could be 1, what would the y value be? 2. So that's going to be an open circle, and we have to choose now some values less than 1. So if x could be 0, which it can, what's the y value? 1. If x could be negative 1, which is legal, what's the y value?
0.
2. So let's put these together. Let's do this one. That's the line 1 that begins at 1, 3, 2, 2, and 3, 1, and continues out here to the right. So that's linear. The endpoint is included. I'm going to come over here and leave this open. 1, 2. Not quite including that point. 0, 1. And negative 1, 2. So there's the piece of the parabola. So we got a part of a parabola, comes up to a point, but excludes it. And then a part of a line that comes up to another point and actually includes it. So what do we want to know? Explain why the function is discontinuous at the given number. Sketch the graph of the function. Now, let's get a quick continuity test. Does the f of, we're checking continuity at x equals 1. Does the f of 1 exist? There it is. Right? When we put 1 into the function, we actually got a y value and we got 3. So we plotted a point when x was 1.
Do you not put in both of them, though?
No, we can't put it in here. I've only put it in here to see what point was omitted.
Okay.
Kind of my almost including point. I almost was able to include 1, 2. But that was deleted. But I was able to include this one because x can be greater than or equal to 1. So that passes our first test of continuity. I think it's going to have a problem here. Do we converge on the same number from both sides of 1? We don't. Here we're getting closer and closer and closer to 2. Up here we're getting closer and closer and closer to 3. So we don't have the same left-hand and right-hand limit. So there is no limit, does not exist, therefore it's what? Discontinuous. Now, if we had gone past, suppose it had a limit. We made it to part 2 of the continuity test. So it had a point that was plotted there. It had a limit as we came in from both sides. What would be next? What's the third step of continuity check? Is the answer to part 1 the same as the answer to part 2? Right? We didn't get there. Is the limit of the function our part 2 answer? Is that the same thing as the point that we plotted? And if you think about it, if the limit is the same thing as the point that you plot, doesn't it have to be continuous? Yeah, you're approaching that value, and then you include that value. It's got to be continuous. So if you just kind of overanalyze the continuity check, I mean, there's no way it could get through all 3 stages and fail to be continuous. All right, let's keep in mind what we still need to look at there from 2.4. Let's begin some new material today. And hopefully tomorrow we'll be able to kind of clean up any other homework questions. So this is section 2.6. Let me put this up here. We're not going to get to all of this today. Every one of these things says the same thing. There's a lot of different ways to look at the slope of a tangent line. And we'll do this first one today. Okay? The tangent line to any function at the point A, f of A, is a line through that point with this slope. So this is the slope of the tangent line. I'll probably summarize that myself. I'll put an M and I'll subscript the little tangent there. But doesn't that look like a slope? Doesn't that look like the difference of 2 y values over the difference of 2 x values? It is. It is a slope. Now let's develop this.
The x approaches A.
X is approaching A, yes. Sorry, that's probably kind of... We'll get that, and I'll point out that it is, in fact, the same thing that I did there. Let's start with a picture. So the first point I want to go to is, and this is some y equals f of x. It could be anything, sine graph, cosine, arctangent, parabola, whatever, some function. And I'm going to come over here to another point. And I'm going to call that the point x, comma, f of x. Now, both of those are points on the original function. Let me start with this. First of all, I know this isn't what we want to finish with, but let's start with the slope of the secant line that contains these 2 points. So I'm going to connect those 2 points on this curve with a line. Call that secant because it cuts through the curve in 2 places. And shouldn't that be the difference of the y values divided by the difference of the x values? Does that look right to you? For those 2 points, did I just subtract y2 minus y1, x2 minus x1? Slope. Now, what would happen if I let the x value get closer and closer and closer to a? Well, a was where I started. X was my second x value. Suppose x gets closer and closer and closer to a. Wouldn't these 2 points get closer together? Right? So as x approaches a, the 2 points that I have pictured get closer and closer and closer together. Now, as that happens, I don't want to clutter this diagram too much, but if the points were practically side by side and you drew that secant line, wouldn't it almost look tangent to the curve if the points were right beside each other? So that's, in fact, what I want to happen. I want to take the limit as x approaches a of this thing right here. And when I do that, the 2 points get closer and closer and closer together. And when this point is right beside my first point, we're not really talking about a secant anymore. We're talking about a tangent. So this is what was that first definition on the sheet that I just took off of the screen. There it is. That is the slope of the tangent. So I'm basically letting the 2 points become 1 point, practically the same point. And I no longer have a secant line, I have a tangent line. Now that's one of the many ways in this section this is presented, and I think it's helpful to look at it in a couple different ways. Now, let me add a couple things here. This is useful. It's not completely useless because we can do better than that and get the slope of the tangent. It's useful. If we want an average rate of change, this is useful. Because it does tell us on the average from point 1 to point 2 what was going on. What was the difference in the y's over the difference of the x's? But sometimes we don't want to know an average rate of change. We want to know what's going on at a specific point. So right here, at this point, what's going on at that point? I don't want to know what's on the average, what's going on from point 1 to point 2. What's going on at point 1, at that point, at that instant? So this is an instantaneous rate of change. Both have their merit. Kind of depends on what it is we want to know. If we want to know a general tendency, a general trend, 2 points is plenty. But if we want to know what's going on at exactly some moment in time that we want to freeze, at time 3 seconds into the flight of this object or into its path, what's happening at that very instant, then we have to use this guy right here. Now, it's not called this yet, but this is our first look at what is called a derivative. A derivative of a function is, in fact, the slope of the tangent line to the curve. Okay, let's look at this example. Any questions about that before I move that? So the key part of this is what I put a star beside right here. See why we look at limits? I mean, a limit is pretty critical here, that we know how to deal with all kinds of different things that happen with limits, because a slope of a tangent to the curve is in fact a limit. JJ.
With the slope, you said that a derivative is the slope of the tangent to the curve, right?
Yeah.
So isn't there unlimited tangents to the curve? So
But
wouldn't
at
there
a
be-
certain point.
Oh, at a certain.
At a certain
oh,
point.
okay.
Then so you're right. If you look at the whole curve, there's a whole bunch of different lines that could be tangent. But if we want to lock into a specific x value, at that specific x value, and you can have curves of a lot of different shapes, at this x value, there's only one slope for that tangent line. But it's probably different than the slope of the tangent line at this x value. So you're right. Curves have variable slope, but we want to lock into one specific place on that curve. So that's what we're doing here. Anything else? That's a good point. If I were a good teacher, I would have brought that up. You wouldn't have had to. Let's see what happens with this. We'll make this our example here today, and we'll finish with this. Let's suppose, and I want this to be reasonably simple. So we'll just take a simple parabolic curve, and let's suppose that we want the equation of the tangent line to this function at a, and this goes back to what JJ said, at a certain x value. We want to lock in to the x value 1. And if we lock into the x value 1, where are we on the curve? We're at the point 1, 2. So a picture, not that you need a picture. So there's our function, x squared plus 1. We're going to come out here to x equals 1. And we want to know the equation of that line that's tangent to the curve. What do we need? Well, what do we have? We have the point of tangency, right? We already know that the point we want it to go through is the point 1, 2. So in finding the equation of the tangent line, we go back to that point slope form. We know the point, so we plug it in. So that's easy enough. What is it that we lack? Besides common sense. I mean, that's just me personally, but we lack the slope. And in fact, don't we want that to be the slope of the tangent line, right? Isn't that what we want? The slope of the tangent line to the curve. What is the slope of the tangent line? It is the limit So based on our first definition, that's how we find the slope of the tangent. Once we get it, we just plug it right back into here. And from that point, in essence, we're done, right? We've got the equation that we want. So what is the f of x? Well, the f of x is, in fact, the way it was handed to us, minus the f of a. What is the f of a? It's a squared plus 1. And down here we've got x minus a, and we want to see what happens as x gets closer and closer to a. That look like I substituted right? F of x minus f of a. all over x minus a. Okay, what happens in the numerator? What's x squared plus 1 minus a squared plus 1? Don't the plus 1s knock each other out? We've got 1 minus 1, and the numerator is x squared minus a squared, thankfully, because we'd have trouble doing this problem if it were not. What's the numerator factor into?
X minus a.
Okay, x minus a, x plus a. Can I slash x minus a over x minus a? Well, I can do that as long as x is not equal to a, right? Are we okay? X is not equal to a?
Mm-hmm.
Not equal to a. It's approaching a, but not equal to a. What we have left is the only remaining term is x plus a, and if x is allowed to get closer and closer and closer to a, what is x plus a?
2a.
Is a plus a, which is 2a, right? Okay, and in this problem, we want our a value to be what specific number? What x value? I mean, a is an x value, right? We want to know what's going on at what x value? 1. So we want a to be 1. So the slope of our tangent line, I don't know if my diagram looks like it, but it does, if I accurately diagram this, it would have slope 2 at that point. And the equation of the tangent line would be that. Is that correct? We already had the point. So all we need to do is find the slope, plug in the specific x value, which was, we're letting x be 1. Slope is 2, and I don't really have a problem with you leaving the answer in this form. You get to this point in this problem, I know that you know what you're doing. So there's really nothing gained by going any further. JJ.
How did you go from the part where it says x plus a and then it equals to 2a? Why is it like that?
We're letting x get very, very, very close to a. So for all practical purposes, x is going to take on the value a. So if I replace x with a, I get a plus a, which is 2a. And what a value do I want x to be? I want x to be 1. Is that okay? Okay, I think I'll wait. Well, would you rather me give you the problem set now? And even though we don't have all the ammunition we need, it's not a long problem set. I think I'll just wait. I'll wait and give you the 2.6 problems after we've completed the material. That'll finish us up from lesson 18.